Hello students, the question is a proton and an alpha particle having equal velocities approach a target nuclei. They come momentarily to rest and then reverse their direction. The ratio of the distance of the closest approach of the proton to that of the alpha particle will be, and the given options are option A 1 by 2, option B 2, option C 1 by 4, and option D 4. So the problem is based upon the topic the atomic theory and nuclei, and in particular an experiment in which alpha particle or some other particle like a proton is projected towards a nucleus. Now the situation is like this. There is a nucleus here. This is the atom, and protons, for example, we take first the case of proton. Proton is approaching towards this nucleus. So now we know that the charge of the proton is plus E, and the mass of proton, let us suppose it is m subscript p, and let the velocity at a particular time instant of the proton is v. Now as proton is approaching towards this nucleus, we know that the charge of the nucleus is plus Ze, where Z is the atomic number. Now since the nucleus is positively charged and the proton is also positively charged, as the proton goes towards the nucleus, there is a force of repulsion between them. They try to repel each other. Now, when the proton is approaching here, its velocity decreases. The velocity of the proton decreases. It goes like this. At a certain final instant, the velocity of the proton, the final velocity of the proton, becomes zero. So, when the final velocity of the proton becomes zero, momentarily, the force of repulsion still exists. So, it reverses its path and goes in the same path but in the reverse direction. So this is the particular case. Now we have to find out the ratio of the distance of closest approach of proton and the alpha particle. Similar experiment is done for the alpha particle and the closest distance approach is calculated. Now in the case of proton, let us call this closest approach distance as RO subscript P, ROP. This is the closest distance. Now since the force of repulsion here acting in this case in the whole situation, this is the conservative force, and for the conservative forces we know that the principle of energy conservation applies. Now in this particular scenario we can apply the principle of conservation of energy, that is the total mechanical energy. Let us call this point as A and call this point as B. So the total mechanical energy at point A is equal to total mechanical energy at point B. Now the total mechanical energy at point A is mainly the kinetic energy. The distance is very much large as compared from the center of the atom. This particular point is very far away, so R is very large, so the potential energy is very small. So the main energy here is the kinetic energy, and we can write the expression for the kinetic energy as half m subscript p, which is the mass of proton, into v square, the velocity square, is equal to, and plus 0 because the potential energy at the point A is 0, is equal to the kinetic energy at point B, which is equal to 0 because the velocity of the particle, the proton, becomes 0 here. So the kinetic energy is 0 plus the potential energy. Potential energy is given by the expression. We know that the potential energy is given by 1 upon 4 pi epsilon naught Q1 Q2 upon R. So this is the formula for the potential energy for two particular charges Q1 and Q2 and at a distance of R. Now here the distance R is ROP. So we can write the expression as 1 upon 4 pi epsilon naught. Q1 here is the charge of proton, which is E. Q2 here is the charge of the nucleus, which is Ze, and R here is Ro subscript P, and it's power 1. So this is the expression for the potential energy. Now we have to find out the ratio of the closest distance approach. So what we do here, we take this particular term ROP in the left hand side by cross multiplying it. So we get this value as ROP is equal to ZE square upon 4 pi epsilon naught M subscript P V square, and this multiplied by 2. 2 is cross multiplied here, and MP V square multiplied in the denominator part, and this ROP multiplied in the numerator part of the left hand side. So this is the expression we get. Now let us call this as equation number 1. Now for the case of alpha particle, if we take the case of alpha particle, so in the case of alpha particle, the change is in terms of mass. Now we know that the mass of the alpha particle is basically four times the mass of proton, and its charge is 2 times the charge of proton. So that's the basic difference for the alpha particle. So applying the same equation for the alpha particle, but changing these parameters, the mass as well as the charge, we get the closest distance approach for the alpha particle as 2 Ze square multiplied by 2 divided by 4 pi epsilon naught 4 mp into v square. Call it as equation number 2. Now we have to find out this ratio ROP upon RO alpha. So when we divide these two, 4 pi epsilon naught cancels with 4 pi epsilon naught, Ze square cancels with Ze square, MP cancels with MP, and V square cancels with V square. So here we get 2 upon 1 divided by 4 upon, this is 4. So this comes out to be 2 upon 1. Or in other words, we can say that the ratio of the closest distance approach for the proton is to alpha particle is 2:1. So option B is correct here. So यहाँ में एक प्रॉब्लम दी गई है, इसमें प्रोटॉन और अल्फा पार्टिकल की बात की गई है. इनकी इक्वल वेलोसिटीज हैं स्टार्टिंग में, और उसके बाद एक टारगेट न्यूक्लियस की तरफ मूव कर रहे हैं, और मोमेंटरली वो रेस्ट पे आ जाते हैं, और उसके बाद अपनी डायरेक्शन को रिवर्स कर देते हैं. हमें निकालना है द रेशियो ऑफ डिस्टेंस ऑफ क्लोजेस्ट अप्रोच प्रोटॉन के लिए और अल्फा पार्टिकल के लिए. तो यहाँ जो बेसिक कंसेप्ट हम यूज करने जा रहे हैं वो है, क्योंकि यहाँ पे कंजर्वेटिव फोर्स है, रिपल्जन फोर्स एक लग रहा है, तो यहाँ पे हम कह सकते हैं कि स्ट्रेट अवे जो टोटल मैकेनिकल एनर्जी है वो कंजर्व रहेगी, और टोटल मैकेनिकल एनर्जी एट पॉइंट ए को हमने बराबर रख देना है टोटल मैकेनिकल एनर्जी एट पॉइंट बी. यहाँ पे जो है एक्सप्रेशन जो है हमारा काइनेटिक एनर्जी प्लस पोटेंशियल एनर्जी के टर्म्स में ही हो जाएगा. काइनेटिक एनर्जी इस पर्टिकुलर पॉइंट पे अगर हम कहें, तो इस पर्टिकुलर पॉइंट पे काइनेटिक एनर्जी होगी हाफ एम पी वी स्क्वायर फॉर प्रोटॉन, एंड पोटेंशियल एनर्जी यहाँ पे 0 होगी. पोटेंशियल एनर्जी का ये जो टर्म हम बात कर रहे हैं, पोटेंशियल एनर्जी जो है वो एक तरह से इलेक्ट्रिकल रिपल्जन फोर्स की वजह से है. इस पर्टिकुलर इंस्टेंट पे क्योंकि डिस्टेंस बहुत ज़्यादा है ए और बी के बीच की, तो इसको हम नेग्लेक्ट कर सकते हैं, जितनी ज़्यादा दूर हो गए. बी पॉइंट पे हम कहेंगे कि मोमेंटरली स्टॉप हो चुका है पार्टिकल, काइनेटिक एनर्जी 0 हो चुकी है, जितनी भी एनर्जी है वो सारी की सारी पोटेंशियल एनर्जी है. तो यहाँ पे पोटेंशियल एनर्जी का जो फॉर्मूला है वो हम अप्लाई करेंगे, U इक्वल्स टू 1/4 Q1 Q2 अपॉन R. यहाँ पे Q1 है चार्ज ऑफ प्रोटॉन, Ze है चार्ज ऑफ न्यूक्लियस अपॉन 4/0, डिस्टेंस है क्लोजेस्ट डिस्टेंस ऑफ अप्रोच इन द केस ऑफ प्रोटॉन. इसे हमने इक्वेशन 1 कह दिया. इसी तरह से हमने इक्वेशन 2 लिखी फॉर द अल्फा पार्टिकल. उसके बाद हमने नॉन इक्वेशंस को डिवाइड किया, तो हम देखते हैं ये रेशियो आता है 2:1 का. सो ऑप्शन बी यहाँ पे करेक्ट ऑप्शन होगा. होप यू अंडरस्टैंड द सॉल्यूशन. थैंक यू.